If we use the ideal gas relationship, we have an equation that says PV is equal to RT. It can also be shown that the internal energy is only dependent on the temperature. So our internal energy U is equal to U at some temperature. When we're looking at specific heat, we have an equation that says our specific heat, CV, is equal to the change in internal energy over the change in temperature. So what we can do with this equation, we can separate it, we can integrate it, so we'll get that du is equal to cvDT. And let's integrate. Well, when we integrate, our bounds of integration are going to be going from U2 to U1 and from T2 to T1. When we perform this, we'll get U2 minus U1 is equal to this integral. So T2, T1, cvDT. We can't do anything more with this unless we make some assumptions. But now let's substitute, because we're working with ideal gas, U is equal to UT. So we'll get U2 is equal to T2. So this is the state 2 minus U1 T1 is equal to, now let's make an assumption that our specific heat is constant. If it's constant, that means it can come outside of that integral, and that integral becomes T2 minus T1. So we'll have CV of T2 minus T1. Now, why is this important? Well, if we remember our first law for a closed system, and we ignore potential and kinetic effects, we have that the change in my internal energy is going to be equal to Q minus W. Okay, so now my change in internal energy is going to be mass times U2 minus U1 is equal to Q minus W. And because, again, we're working with ideal gas, it's going to be this mass of U2 T2 minus U1 T1 is equal to Q minus W. All right, so this is my energy equation for a closed system. And you can see that we're just able to substitute this with this. So we can get the equation that M CV T2 minus T1 is equal to Q minus W. So we can use either of these two equations. In this equation, we need to know what our constant specific heat is. So we could look that up from a table. Granted, we know at what temperature. And on this one, we would need to look up both of U1 and U2. So U1 and U2 would also come from tables. It would come from a different table than CV, but it would come from a table. Again, granted, we knew what T1 and T2 are. But in each of these cases, we need to know our temperature. We need to know T2, T1, T2, and T1. So now what I'd like to do is work the following problem. So we have that air is compressed adiabatically from P1 is equal to 1 bar, T1 is equal to 300 K, to P2 is equal to 15 bar, V2, our specific volume, is equal to 0.1227 cubic meters per kilogram. If we assume ideal gas, we want to calculate the work in kilojoules per kilogram using a table, and also assuming constant specific heat at 300 degrees Kelvin. So the other assumption we are going to make is that we're going to ignore kinetic and potential effects. And just like I was just saying, let's clean this up a little bit so I have some room to work. But in this particular problem, they're asking for kilojoules per kilogram. So mass is going to be divided over here. We're not going to have mass on this side. And because it's adiabatically compressed, that means in this process, Q is going to go to 0. There's no heat transfer. All right, so now let's figure out what T2 is. And we were using ideal gas, so we have P2, V2 is going to be equal to R T2. We can solve for T2. We can say T2 is equal to P2 V2 over R. P2 is going to be 15 bar. V2 is equal to 0.1227 cubic meters per kilogram. And then we have R. So R is, let's do it with the gas constant. So 8.314, and this is going to be a kilojoule per kilomole Kelvin. And we want to divide this by the molecular weight, and we need to get M. So M comes from a table. So this table is table A1, and it shows that M, which is our molecular weight, is going to be 28.97. And its units are kilogram per kilomole. All right, now let's do a quick unit test. We're going to have to do some things with the bar. So for 1 bar, this is going to be 10 to the 5th Newton meters squared. And 1 kilojoule is going to be 10 to the 3rd Newton meters. When we check everything, kilomole cancels with kilomole, kilojoule cancels with kilojoule, bar cancels with bar. Those are the easy ones. Then the Newton over here is going to cancel with that Newton because it's going to flip because of this fraction. This meter cubed is going to combine with this meter cubed, or meter squared. This meter is going to combine with this meter squared, which is then going to cancel with this meter cubed. This is going to be left, so that's good. We know that we're going to be having at least Kelvin. And then the kilogram, what happens here? The kilogram cancels with that kilogram. And this 10 to the 3rd cancels with this, so we are left with 10 squared. And that should be it. Yep, so let's put that in the calculator. And with the calculator, we get 15 times 0.1227 times 100 divided by 8.314 divided by 28.97. So we get our temperature, T2, is equal to 641 Kelvin. We'll just say 641. All right, so now we're doing the tabular approach first. So we're going to use this top equation. We need U2 of T2 minus U1 of T1 is equal to minus W. Okay, we can solve for W, so we'll get minus U2 plus U1, or if we rearrange that, we can get U1 T1 minus U2 T2 is equal to my work. So where do we go to get these values? Well, because we're working with air, we want to go to table A22. All right, so let's go to our air table. And how this table works is like this. The first column right here is going to be our temperature. Then we have enthalpy and we have internal energy. So that's what the two columns that we're interested in this problem. We don't care about this column. We don't care about the enthalpy. We don't care about our entropy stuff. We don't care about those columns. But there's a lot of temperatures. So then this column right here is just sort of the extension of the column. So the temperature goes from 200 to 400, and then it wraps back around here and it goes to the 450 through 740, and there's more pages that I just didn't copy. So the table continues to wrap on itself, and again, we're not interested in this column. We're interested in these two columns. That looks ugly, but hopefully I won't pick a wrong value. So now what do we need? We need U1 at T1. So this T1 is 300 Kelvin. So we're over here. 300 Kelvin is 214.07. So this is going to be 214.07 minus the internal energy at T2. Well, T2 is, we found it, this 641. 641 is somewhere between the two values of 640 and 650. So we're going to need to linearly interpolate. So we're interested for our internal energy, U, at 641 Kelvin. Okay, now our two entries, our low entry is 640, so we're going to look at that. Our internal energy at 640 is 465.5. Now this is equal to the entire range, so 650 minus 640 divided by the entire range, so 473.25 minus 465.5. Okay, so then let's do that calculation. And we'll have 473.25 minus 465.5 divided by 10. Well, then really times 1 plus 465.5. So it should be close to 465.5. And I get that this is equal to 466.3. Okay, so then we're going to subtract 466.3. And that's going to give me my work. So my work is going to equal to 14.07 minus 466.3 minus 252.23. And I had forgotten when I rewrote this, but this is really work per M. So this is going to be, what are these units? It's a good... so we do know that this is a unit of kilojoules per kilogram, and that makes sense. So this is going to be 252.23 kilojoules per kilogram. Okay, so now let's look at the constant specific heat approach. With the constant specific heat, we're going to get rid of this table, And instead, we're going to start by looking at the equation we have here. So CV of T2 minus T1 is equal to minus W over M. Okay, let's rewrite that. So it's going to be CV of T1 minus T2 is equal to W over M. We can get a little more space. So I know everything except for what CV is. And we're told to use constant specific heat CV at 300 Kelvin. So let me look at my table that will give me my specific heats. In this table, you have different substances and different gases. So in this case, it goes down, it extends. I had just cut it off, but we have air. So then we have a constant specific heat, CP. We have a constant specific heat, CV. We're not using CP right now. We're using CV because we're worried about the CV. CV is related to the internal energy. So now we just have to figure out what it is at 300 degrees. This is 300 degrees. Tough to see, but if I can get up there, 300 degrees, my CV is 0.718. So I can go over here and I can say, all right, this is equal to 0. Let me do it here, and 0.718. The units are kilojoules per kilogram Kelvin. And then I just need T1 and T2. T1 is 300K. T2 is 641K. So the K's are going to cancel with this. And again, I get kilojoules per kilogram. And I'll get 718 times 300 minus 641. I'll get this is equal to minus 244 kilojoules per kilogram. The two answers are pretty similar. This is probably going to be your more accurate approach, since this is making the assumption of a constant specific heat. And it also depends on how well your problem is modeling an ideal gas. While these are just more property tables like we would have with other substances that we've looked at. So hopefully this video has showed you the two different approaches you can take, whether you take the tabular method or a specific heat method, and how to go about them.